Welcome to the e-Pathshala lecture series on computer science. This is the 14th module of the course Computer Graphics and Visualization. So we have had last 13 sessions in the past. In the previous session, we have learned how 3D objects are represented, and in this session we are going to look at 3D transformations as the topic. Okay, let us proceed with the content of the today's module. These are the people who have contributed to this course, and let us look into what we are going to see today in this session. Our aim or objectives are to understand the 3D transformations, which include translations, rotation, scaling, shear and reflection. The other transformations like transformation between coordinate systems also will be learnt in this session. So let us look at each of these in detail. So in this, the first and the foremost thing that you should learn is the convention. So what are the conventions in computer graphics as far as 3D graphics is concerned? So imagine we are in a 3D world. So like we need to understand some conventions are fundamental, which are fundamental to understanding how things happen in the 3D world. Let us take say a coordinate system in 3D world. So as we know, a coordinate system in 3D world is made up of three coordinate directions, or three mutually perpendicular directions, which are the x, y and z. Now we know that we can imagine the coordinate system at various positions, at various in various orientations and so on. So for this we need to know some conventions. So let us imagine, or let us consider our right hand. Okay, so take our right hand, open, that is the three mutually perpendicular directions, and how do we get as convention from the right hand is take the first three fingers of your right hand, the thumb, the index finger and the middle finger. Now let the middle finger point towards you, the self. Okay, let the index finger point upwards, let the thumb point in the right hand direction, that is right side, because this is our right hand. The thumb points the right side, the index finger points upwards and the middle finger points the self. So these three directions are considered as the positive x, y and z directions respectively. That is, the thumb points the positive x direction, the index finger points the positive y direction and the middle finger points the positive z direction. So the opposite of this, that means it is important that you should understand that we are seeing into the world along the negative z direction. An important observation is that because the middle finger is pointing towards the self, which is the positive z direction, and we are looking into the world along the negative z direction. So that is the convention that you should remember. Always we look into the 3D world in the negative z direction. So if you take your left hand for that sake, you can formulate similar coordinate system which is something like this. Okay. So here for our understanding, it is enough that we consider one convention, which is say the right handed coordinate system. So the difference here is that in 2D and 3D, in 2D we do not need to consider such conventions, but in 3D we need to consider such important conventions. So the transformations in 3D are, which are fundamentally object transformations, which are extensions of transformations in 2D. Let us start with the first and the foremost transformation in 3D, which is translation. As we know, translation, rotation and scaling are three fundamental transformations. Followed by that we have the other transformations like reflection and shear. So let us start with the very first transformation in 3D, which is translation. Translation is simply change in position, as we know from the 2D transformations, and we have got an extra coordinate direction and an axis, extra axis here. So we need to add for the matrices an extra row and column. So thereby we have we see all the matrices that we see for the transformations are all 4 by 4 matrices because of the homogeneous coordinate system. Inclusion of the homogeneous coordinate system, we have 4 by 4 matrices for any transformation in 3D. Okay. So if we start with translation, translation is change in position of an object. So take an object in 3D and move it to another position, so it is translation. So, it is a simple extension of 2D translation with an addition of one more direction, which is the z direction. So, the equations are very much evident, as you can see. X dashed is given by x plus tx, x dashed is the new x position, y dashed is the new y position, and z dashed is the new z coordinate or the z position, and tx, ty, tz are the translational distances along x direction, along y direction, and along z direction, or how much you move along each of these directions are the tx, ty, tz. So, that is where the matrix is also you can easily formulate, as you can see there, x dashed, y dashed, z dashed 1 is equal to 1 0 0 tx, 0 1 0 ty, 0 0 1 tz, and the last row happens to be the 0 0 0 1 for the homogeneous coordinates. So, multiplied with the initial position x, y, z and 1. So, that is a simple extension of a 2D translation. But rotation in 3D is much more complex than rotation in 2D. If you look at 3D rotation, it involves rotations are understood to be done about standard coordinate directions initially. So, for example, say for rotation we would require an axis of rotation. Okay. In 2D, if you correlate that with 2D, try to always like link your thing with 2D. Whenever we are discussing something about 3D, you can link that with 2D as well. In 2D, for rotation, we require a single point of rotation, or maybe a position for rotation, which is called the pivot point. But in 3D, we would require an axis of rotation. That means an object is considered to be rotating about an axis. An axis here is any infinitely extended line. For our initial level of understanding, the axes that we would consider are the 3 coordinate directions, or the 3 standard axes, the x, y and z respectively. So, rotation about x axis, so rotation about y axis and rotation about z axis. So, if you see the names given in the technical names, for rotation about x axis is pitch, rotation about y axis is yaw, and rotation about z axis is roll. Now, which rotation is considered positive, which rotation is considered negative? As you can recollect the discussion on 2D rotation, you have rotation with respect to, that is rotation with respect to any point in space, and in the anti-clockwise direction is considered positive. Any rotation which is considered in the anti-clockwise direction about a pivot point in 2D is considered as positive. But now, how do we consider positive rotation in 3D? Okay. So, for that again there are conventions. The conventions again which are shown here, the conventions are such that when you are standing and watching the object getting rotated in anti-clockwise direction about an axis, and you are actually looking along the negative direction of that particular axis, and that is the positive rotation. Again, let me repeat this. You imagine you are standing and you are along a particular axis. Imagine you are along a particular axis. So, you are on some axis, say x, y or z. Okay. If now you imagine that you are standing on the axis and viewing the axis along the negative direction, that is your view is along the negative direction of that axis. That means if you are standing on x axis, you are actually looking at the negative x axis, the direction of view is the negative x axis, and consider an object being rotated about the axis in anti-clockwise order. Consider the rotation about the axis when you are viewing the negative direction of the axis and in the anti-clockwise direction. So, that is considered as positive rotation. So, similarly, if you have to consider positive rotation about y axis, imagine you are standing on y axis and you are looking at the negative y direction, and now the anti-clockwise rotation about the axis is considered positive. So, otherwise the clockwise rotation is obviously the negative rotation. So, these are the important conventions, and the z is just as similar to any other axis. First, we will understand how the z axis rotation is done. So, z axis rotation is, imagine you have an axis passing through origin and is perpendicular to the coordinate system. So, that is what we know as, imagine you have a plane like object, plane like thing, and your z direction is actually the direction that is perpendicular and is passing through the origin of the coordinate system. Now, it is exactly similar to, that is the rotation in 2D, it is the 3D rotation about z axis is exactly similar to rotation in 2D with respect to origin. Now, let me relate these two again, let me repeat this. Z axis rotation in 3D is exactly similar to rotation in 2D about origin, how it is. Now, the z axis rotation is what? That is rotation about z axis. Now, how do we do this? That is, what is positive rotation there? It is nothing but when you are seeing along the negative z direction, that means you can imagine again the three mutually perpendicular directions, the x, positive y and positive z for the right handed coordinate system, and now you are viewing along the negative z direction. Now, imagine this rotation that is an anti-clockwise rotation is considered positive. So, if you look at the equations there, the z coordinate has not undergone any change. X dashed is equal to x cos theta minus y sin theta, same equation for 2D which we saw, the same equation exactly, and y dashed is equal to x sin theta plus y cos theta, and z dashed is z. Now, what has happened to z coordinate when rotation about z axis is being performed? Now, the question is, what happened to the z coordinate when the rotation is being performed about z axis and is positive? Is that there is no change in the z value, but the x and the y values have changed. So, that is, whenever we perform rotation about a particular axis, say assume now x axis, okay, when you are rotating about x axis, the y and the z will change, but the x will remain constant. When you are rotating about y axis, the x and z will be changing while the y remains constant. So, these equations, now there are three, and the corresponding transformation matrix in 4 by 4 form is given there, which is the homogeneous transformation matrix. Cos theta minus sin theta 0 0, sin theta cos theta 0 0, and 0 0 1 0 and 0 0 0 1 is the matrix. Okay, so it is shown there, I think, in a diagram, as you can see there in a diagram which shows what is positive. So, when you are viewing along the negative z direction, the anti-clockwise rotation about that axis is positive, which is indicated with the matrix, which is indicated with the notation R rotation, Z axis, theta is the angle of rotation. Now, to get to derive matrices or equations for rotations about other two directions, like other two axes, say x and y, you do not have to really derive equations, but rather with a thumb rule you can simply formulate the matrices or the rotation transformation matrices for rotations about the remaining two axes, the x and the y. How can we do that? Is with a simple thumb rule, as you can see there, x to y, y to z, and z to x. So, this thumb rule you remember, x to y, y to z, z to x. That means you take the first set of equations for rotation about z axis, okay, and in those equations you replace x with y, y with z, and z with x in the equation set of equations. You will automatically obtain rotations about the other axis. How that is you can watch this here, and x dashed is equal to x cos theta minus y sin theta, y dashed is equal to x sin theta plus y cos theta, and z dashed is equal to z. So, these three equations are what are rotation about z axis. Now, how do we get the rotations about x axis and y axis? Is simply wherever there is x in this equation, first set of equations, take the replace them with y, y with z, and z with x. So, now first equation becomes y dashed is equal to y cos theta minus z sin theta, which is there in the second equation in the second diagram. Z dashed is equal to y sin theta plus z cos theta, which is the replacing y with z, z with x, x with y. So, that is the thumb rule. And finally, for z dashed is equal to z, z to be replaced with x. So, x dashed is equal to x. So, when x dashed is equal to x, that means there is no change in the x values. It is understood that the rotation is performed about x axis. So, for that you can easily formulate a matrix when you write x, y and z, that is x dashed, y dashed and z dashed in that order. Now, rotations about y axis similarly can be formulated, can be transformation matrix can be easily obtained by rewriting these equations for x axis rotation and using the thumb rule, that is replace x with y, y with z, z with x, and so that is how you get the third set of equations which are rotations about y axis. Now, the two matrices are given, they are easily, like you can formulate and write the equations in the order x dashed, y dashed and z dashed, so that you can formulate the homogeneous transformation matrices. Observe the notation used. R suffix x of theta, okay, is the x axis rotation. R suffix y of theta gives the y axis rotation, and the diagrams are self explanatory, you can just have a look at them, you will understand better. So, if we require to perform a rotation in 3D, what is that we assumed is we require an axis of rotation and an angle of rotation. Now, the axis of rotation here, if we imagine that to be any general line or direction in space, we can imagine, okay, any line in space can be an axis for rotation. So, that need not be the coordinate directions x, y and z, it can be any imaginary direction in space. So, let us assume a scenario where we need to perform rotation about, say, an axis which is parallel to x axis as shown in the first diagram there, okay, that you are seeing. Rotation about an axis which is parallel to x axis. Now, what is the extra step required? So, what is that, how the matrix transformation matrix would be? Again, that would be a composite matrix. As you can remember from the discussions in 2D transformations, we had composite transformations. Now, similarly, what is that we are going to do here is we are going to take the rotation axis, that is, imagine any direction. Here our axis of rotation is a line parallel to x axis. Now, what is the first step? Our aim is to actually bring this axis onto any of the unknown directions and apply the rotations with respect to those known directions, and then put the axis back at their original position. That is the usual procedure. So, let us translate the axis, which is the rotation axis, onto either of the known axes like x, y, z. For convenience, we can simply translate that axis onto x axis, so that it coincides with x axis. Now, perform a rotation with respect to x axis, and now translate the axis back to its original position. So, that is a composite transformation, and you can see the equations. P dashed is equal to, you can come in the reverse order always, a translation, a rotation about x axis and a translation inverse. So, that completes translation here. So, you can read the steps here. So, in general, if you have to perform rotation about any general direction in space, so now we have gone to a more complex scenario, that is, the rotation axis is no more a coordinate axis or is neither a line parallel to the coordinate axis. It is some randomly oriented line in space. Now, how do we perform rotation of objects about that kind of axis? So, we need to perform so many steps, as you can see from here. What is that we are doing is, imagine an axis of rotation is given there, shown in the red dotted line, and that is a randomly oriented axis, now about which we need to now rotate objects. So, now what would be the rotation matrix for such a kind of complex scenario? Now, in this scenario, imagine 2 points on this randomly oriented axis in space, which are, say, P1, P2. So, P1, P2 are 2 points identified on the line. Now, perform a translation such that P1 is brought onto the origin. So, that means we are basically translating the line such that the line now passes through origin, that is, the rotation axis that is randomly oriented initially now passes through origin. What is the next step? The next step is perform a rotation about x axis first. So, again let me repeat this. First you do a translation so that the line now passes through origin. line passing through origin does mean that a point on the line that we have considered is to be translated so that the line automatically passes through the origin. Now that becomes now P1 dash P2 dash are the 2 points. Now perform a rotation of this random axis about x axis till the time that the line now is in the plane xz. So that means you do a rotation of this line about x axis till the point it is a part of, or it falls into the xz plane. Okay. So that is the important step here. So by what angle you should rotate is again a lot of mathematical derivation that goes there. So imagine for the time being you need to rotate that first about x axis so that the line now falls into the xz plane. Now perform a rotation about y axis now such that the line in the xz plane is now rotated till the point that it aligns with the z direction. Always our aim is to align anything, any randomly oriented line with the z direction. Okay. Now the second rotation is with respect to y axis and you align that with the z direction by some angle, if you rotate by some angle. So the next step is to perform rotation about z axis. The standard rotation about z axis, which is r z of theta. The standard rotation matrix is x dashed is equal to x cos theta minus y sin theta, y dashed is equal to x sin theta plus y cos theta, and z dashed is equal to z are the set of equations that you can consider. The matrix for that you can assume. Now after this rotation is done, simply go in the reverse order. So first do a rotation about y axis in the reverse by the reverse angle, that is the opposite angle for the angle that you rotated. Next do a rotation about x axis in the opposite angle and do a translation. So the steps are complete. So the matrix, the final composite matrix for the rotation about any general arbitrarily oriented line or randomly oriented line in space is the matrix T inverse, Rx inverse, Ry inverse, Rz, Ry, Rx and T. When you combine all these, what you get is the composite matrix. The 3D scaling involves just an extension of 2D scaling, an additional third coordinate or third scaling factor along the z direction, which is Sz, and the rest is all the similar thing. And reflection in 3D is exactly similar to the reflection in 2D. But here what is happening is reflection in 2D was being performed with respect to lines. Now in 3D reflection will be performed with respect to planes. Reflection in 2D was being performed with respect to lines, and reflection in 3D will be performed with respect to planes. So reflection with respect to xz plane, reflection with respect to xy plane, reflection with respect to yz plane, and so on. Now the matrix that you can see for reflection with respect to xy plane, what is happening? Imagine an object here and this is the xy plane. Okay, imagine an object here and this is the xy plane. Okay, this is the xy plane and this is the negative side of the plane, that is the negative z direction. Now this object has to be reflected, and so that it is here now. Okay, this is the plane, this is the object, and this object is now here after reflection. So what is happening to the object is its x coordinate is not getting changed, its y coordinate is not getting changed, its z coordinate is getting, it's in the negative side now. So that is why the matrix has got a -1 in the third row and the third column position, where it is called z is equal to z, xy is equal to 0 is nothing but this is z is equal to 0 plane. We call the xy plane as the z is equal to 0 plane. Okay. So the z coordinates alone become negative. So shear in 3D is an extension of shear in 2D, where we have got the coefficients a and b as extra coefficients in that the extension of 2D, where b is the additional coefficient, and it is shear with respect to the z is equal to 0 plane, or here we consider not axis but the planes here for shear. So with this we come to the end of this module. Here the summary is that what we have learned here is that what are the conventions for a coordinate system in 3D. The right-handed convention, the right-handed coordinate system, you can imagine Rotations in 3D are the complex things, then and the other rest of the transformations are exactly extensions of that in 2D. So, this is what we have learned here, and reflection and shear are other transformations which are simple extensions of 2D transformations. Instead, we consider that is called planes than axis for reflection and shear. The source for this book is the Hen and Baker Computer Graphics with OpenGL is the source for the book, for the module. Okay. Thank you for being with the session.